Across the entire sky, a nearly uniform background of ancient light is present, arriving today as microwave radiation with a temperature a little under 3 Kelvin. This field is the cosmic microwave background, the cooled remnant of the early universe, when matter and radiation were tightly coupled and then separated as the first atoms formed. Its uniformity is high, but not exact. Small variations in brightness and temperature are spread across the sky, described as anisotropies. On large angular scales, these variations look like soft undulations rather than sharp spots. They are measured in microkelvin, which is a millionth of a Kelvin, and they trace a combination of early-time acoustic structure and late-time effects that light accumulates as it travels through evolving cosmic structure. The full sky image is often expressed in spherical harmonics, where the largest features correspond to the lowest modes. Within this calm map, one region stands out as unusually cold. When averaged over a large circle, a patch in the direction of the constellation Eridanus, commonly called the cold spot. A temperature map is a measurement made by scanning the sky, with instruments that compare the brightness of the microwave background in many small pixels. After correction for motion of the observer and for foreground emission from the Milky Way, the remaining pattern is a set of small coherent fluctuations. The Eridanus region appears as a roughly circular area where the temperature is lower than the surrounding average when smoothed on a scale of several degrees. The word degree here refers to an angle on the sky, the same way the moon spans about half a degree. The cold spot is not a point feature. It has an inner depression and a broader gentle ring where temperatures rise toward the mean. The amplitude of the central depression is small in absolute terms, measured in tens to a few hundred microkelvin, but it is large compared with the typical fluctuation at that angular scale in the standard picture. This contrast raises a specific question that guides the outer to inner path of the narrative: is the feature a statistical low in a random field drawn from the standard model of cosmology, or did the light that passed through that direction encounter a corridor of matter that altered its energy on the way to us? The standard model of cosmology, often summarized by a mixture of cold dark matter and a cosmological constant, sets expectations for patterns on the sky. The early universe imprints a primary spectrum of anisotropies, whose properties are fixed by the initial conditions and by the physics of the plasma before atoms formed. Later, as cosmic expansion accelerates, gravitational wells and hills, formed by large-scale structure, evolve in time. Photons that cross regions whose potentials decay or grow can gain or lose small amounts of energy. This secondary process is called the integrated Sachs-Wolf effect. It acts along long lines of sight that pass through underdense or overdense regions at redshifts where cosmic acceleration matters. The Eridanus direction lies across a substantial stretch of the nearby universe, where galaxy surveys show a deficit of galaxies compared with the cosmic average. Such a deficit is a tracer of an underdensity in matter sometimes called a void when large and deep enough, and a supervoid when it encompasses multiple connected voids across hundreds of millions of light years. A map of temperature alone cannot identify the cause of a cold region. The next layer of observation checks whether the sky toward Eridanus aligns with an underdensity in the three-dimensional distribution of galaxies. Wide surveys count galaxies as a function of direction and estimate their distances through colours that correlate with redshift. When these counts are smoothed across large windows, the Eridanus corridor shows a depression relative to fields at similar galactic latitude. The depression extends across a broad range in distance, not as a single empty sphere, but as a connected sequence of lower than average densities. In the cosmic web, matter arranges itself into filaments, sheets, clusters, and voids. The line of sight toward Eridanus crosses more void-like volumes and fewer massive clusters than typical directions. This pattern supports the idea that the microwave photons traversed evolving under dense structure and could have been shifted to slightly lower energies. The path length through which such energy shifts accumulate matters. The cold spot's angular size on the sky translates for typical distances of the nearby universe into a corridor that spans hundreds of millions of light years. A single spherical void of that size and depth is not the only possibility. A nested sequence of voids aligned along the sightline can produce a similar integrated effect. The key parameters are the density contrast, which is how far below the average the matter density falls the radial profile, which describes how the deficit changes from centre to edge, and the redshift range over which the deficit persists. Observations indicate a broad, relatively shallow underdensity with substructure rather than a perfectly symmetric empty bubble. From the outer perspective taken here, this is sufficient to justify deeper questions about how much of the observed temperature decrement could rise from the line of sight structure, and how much belongs to the random draw of the primordial field. Large-scale microwave maps are also affected by foregrounds. Dust in the Milky Way emits at microwave and sub-millimeter wavelengths, and radio galaxies add compact sources that can bias temperature estimates if not masked. The Eridanus direction lies at a latitude where galactic emission is present but manageable with standard cleaning methods. After cleaning, the residual cold patch persists. This persistence does not prove a physical cause along the line of sight, but it removes some obvious alternatives. Careful analysis then compares the cold spot's profile with that expected from a combination of primordial fluctuations and the integrated effect of a supervoid. The outcome of such comparisons depends on the assumed shape and depth of the matter deficit, and on the precise cosmological parameters that set how potentials evolve. Within current uncertainties, the integrated effect can contribute a part of the signal, but the full depth of the cold spot remains difficult to explain with a single simple void. This is a guide rather than a verdict. It suggests that any line of sight contribution comes from a complex extended underdensity rather than from a lone deep cavity. The transition from a map of galaxies to a map of mass is made with lensing. The gravitational field of matter bends light from more distant sources, altering their shapes, and in the case of the microwave background, altering the pattern of small-scale anisotropies in a way that can be reconstructed as a lensing convergence map. An underdensity along the line of sight should produce a negative convergence signal. Measurements of lensing toward Eridanus provide an independent check on the presence and scale of a mass deficit, without relying on how galaxies populate the underlying matter. The lensing signal is subtle, because the underdensity is broad and the distortion is weak. Still detecting a consistent deficit strengthens the case for a physical corridor that could imprint a small secondary temperature shift. Observations cannot yet fix every detail. Distance estimates from galaxy colours have errors that blur structure along the line of sight. Masks that remove bright radio sources can preferentially eliminate regions near the cold spot, and bias counts if not modelled. Foreground dust corrections carry their own uncertainties. Despite these cautions, the overall picture remains coherent when seen from the outer scale. A cold region on the microwave map aligns with a broad underdensity in galaxy counts, and lensing measurements do not contradict the presence of a mass deficit. The amplitude of the microwave depression is larger than a simple single void would produce in the standard model, but the direction, sign and scale of the effect are consistent with an extended evolving set of underdensities contributing to a part of the observed pattern. In this first sky-wide frame, the Eridanus cold spot is therefore placed as a large angular feature in the microwave background, with a coherent colder than average centre and a surrounding ring of milder temperature. It sits along a line of sight where the cosmic web appears less crowded than usual across a long path. The standard cosmological model predicts that such a path can shift photon energies slightly through evolving potentials. The measurements suggest such a contribution is plausible but incomplete. Foregrounds have been reduced and known systematics are tracked, yet absolute certainty about the full cause remains out of reach at this scale alone. That is the correct place to pause in an outer to inner path. The sky map sets the stage. The statistical expectations are recalled and the line of sight context is established. The next step narrows to define how voids are measured and classified, how a supervoid differs from smaller underdensities, and how those measurements along the Eridanus corridor translate into a profile that can be compared quantitatively with the temperature depression seen on the ancient light. A void is a region where the matter density falls below the cosmic mean when averaged across a chosen scale. The definition depends on scale because the cosmic web is layered filaments, and sheets enclose small hollows, which in turn nest inside larger depressions. To make the term precise, surveys smooth the galaxy distribution over spheres or ellipsoids of set radii, and compute the density contrast, which is the fractional difference between the measured density and the mean. A typical void in galaxy surveys spans tens of millions of light-years, with a central contrast that can be several tenths below the mean. A supervoid is a broader connected underdensity, whose effective radius can reach hundreds of millions of light-years, and that may contain a complex of smaller voids separated by low ridges rather than a single smooth bowl. In this classification, the Eridanus corridor is investigated as a supervoid candidate, because the deficit in galaxy counts covers a large angle and appears to persist across a wide span in distance. The measurement begins with a catalogue of galaxies that covers a large fraction of the sky with uniform depth. Two kinds of distance estimates are common. Spectroscopic redshifts provide precise distances but are available for fewer galaxies because they require longer observations per target. Photometric redshifts estimate distance from broad colour information and reach many more galaxies with larger uncertainties along the line of sight. For mapping supervoids, the large number of photometric redshifts is valuable because the structures of interest are broad enough that modest radial blur does not erase them. The sky is divided into angular pixels, and within each pixel, the number of galaxies is counted in redshift slices. The counts are then compared with the survey's average at the same redshift to form a map of over and under densities. Smoothing these maps with kernels matched to void scales produces a field where extended depressions stand out. Identifying a supervoid requires more than noting a minimum in the smoothed field. The depression must be coherent across neighbouring pixels and persist across adjacent redshift slices, rather than appear as a single slice artifact. Algorithms trace connected regions below a chosen density threshold, measure their volumes in angle redshift space, and fit simple profiles to their radial structure. Two properties are central. The first is the effective radius, which is the radius of a sphere with the same volume as the connected underdense region, after accounting for the survey mask. The second is the density contrast profile, which describes how the deficit varies from the centre to the edge, and whether the region shows compensation, which is a mild overdense shell around the underdense core. Compensation matters because it influences how evolving potentials change photon energies. A deep core with a strong compensating wall can reduce the net imprint that a simple underdensity would have produced. The Eridanus corridor shows a broad, shallow depression when mapped in this way. The deficit does not drop to zero density. It is a graded underdensity whose centre is lower than average and whose edges rise gently toward the mean, with indications of mild compensation in some redshift ranges. The effective radius inferred from fits depends on the chosen threshold and on how the profiles are parameterized, but it falls into the regime expected for supervoids rather than for ordinary voids. The redshift extent is wide. The depression begins near the local universe, continues through intermediate distances, and fades as the line of sight reaches layers where the survey depth and galaxy population change. The shape in redshift is not a single symmetric trough. It is a set of overlapping deficits whose sum produces a broad corridor of low density. A profile that connects to microwave data must be expressed as a matter under density, rather than just a galaxy count deficit. Galaxies are biased tracers of mass. They are more likely to form in overdense regions and less likely in underdense ones. The bias factor depends on galaxy type and redshift. Converting counts to mass requires modelling this bias and the survey selection function. The modelling introduces uncertainty, but over large scales the conversion is stable enough to assign an approximate matter contrast to the Eridanus corridor. With this contrast in hand, one can compute the expected integrated Sachs-Wolf contribution from the evolving potential of the supervoid. The result depends on the cosmological background because the growth or decay of potentials at late times is tied to the acceleration of expansion. In a universe with a cosmological constant, deep extended underdensities at modest redshift can produce a small cold imprint, whose amplitude scales with the product of depth and width of the potential, and whose profile on the sky follows the projected density profile convolved with the beam of the microwave map. Stacking analyses offer a way to judge whether underdensities in general produce the expected imprint. Many voids selected across a survey are aligned and averaged on the microwave map. The mean temperature profile around their centres is measured and compared with the random stacks. These studies detect small coherent signals that match the expected sign. Void-centered stacks are slightly cold, and cluster-centered stacks are slightly hot. The amplitude of the mean signal is modest, and the spread about the mean is large. Against this background, the Eridanus cold spot sits as an outlier in amplitude, while being aligned in sign and scale with the underdensity. The implication is that while the supervoid corridor could contribute part of the cold region, the total depth of the cold spot remains high, compared with the mean effect expected from voids with similar parameters in the standard model. This does not demand a new mechanism. It marks the feature as uncommon, and directs attention to careful checks on both the void profile and the temperature map. Weak lensing supplies such a check. The matter deficit should leave a negative convergence signal in maps that reconstruct the projected mass from distortions of background galaxies or from the microwave background itself. Because the Eridanus corridor is wide and shallow, the lensing signal is expected to be low in amplitude and smeared by the same photometric uncertainties that blur the redshift profile. Even so, analyses that target the corridor report consistency, with a broad low convergence patch rather than a strong compact deficit. This supports the picture drawn from galaxy counts. The structure is extended and gentle. It argues against explanations that require a narrow, deep void positioned at exactly the right distance to maximize the effect. The measurements favour a corridor composed of multiple underdense layers that together produce a long, low trough. Foreground systematics remain a parallel concern. The galactic plane is a source of polarised and unpolarised emission at microwaves. The Eridanus direction lies away from the very brightest foregrounds, yet masks and cleaning methods still matter. Radio point sources that sit inside the cold spot region must be removed or their fluxes modelled. Faint dust emission gradients must be accounted for with templates. Modern maps perform these steps and report residuals. The cold depression remains after cleaning, and its profile is robust against reasonable changes in masks and foreground models. On the galaxy side, spatial variations in survey depth, star-galaxy separation quality, and photometric calibration can imprint artificial density patterns that correlate with galactic latitude. Careful analyses measure these systematics using random catalogues and by cross-checking with independent surveys. After correction, the underdensity toward Eridanus persists, though its precise depth and compensation vary within uncertainties set by those corrections. Within these bounds, a quantitative path emerges. The supervoid corridor contributes a cold signal aligned with the observed cold spot. The amplitude attributable to the corridor falls short of the full depression in many reconstructions, but not by a decisive factor that would rule out a significant contribution. The remaining gap can be assigned to the primordial fluctuation field that the microwave map records from the early universe. In that hybrid picture, the cold spot is partly a statistical low at large angular scales and partly a corridor-induced decrement from late-time structure along the line of sight. The division between these parts is not uniquely fixed by current data, because the conversion from galaxy counts to mass carries bias, and because lensing maps at the required scales are still noisy. The combined evidence, however, argues against singular exotic causes at this stage, and keeps the explanation within known physics a rare draw, from the early field enhanced by a long underdense path at late times. The next layer of description focuses on geometry. A supervoid can be approximated by simple radial profiles when computing its integrated effect, but the Eridanus corridor is not spherically symmetric. It is elongated along the line of sight because of the redshift span and patchy an angle because of embedded filaments and sheets that cross it. Models that use compensated top hat profiles provide a baseline. More refined models replace the top hat with smooth profiles that allow shallow central slopes and gentle edges. For the corridor, a model built from a sum of such profiles at different redshifts, each with moderate contrast and partial compensation, matches the three-dimensional maps better and produces an integrated signal that aligns more naturally with the measured temperature profile at cold center, with a weak surrounding ring where compensation slightly warms the sky. The classification of the Eridanus structure thus rests on several measurable quantities, an effective radius in the supervoid range when projected on the sky, a moderate central matter deficit, when bias corrections are applied, partial compensation at some depths, and a broad redshift span that turns the line of sight into a layered trough. Each of these quantities carries uncertainties that are reducible with deeper surveys and tighter photometric calibrations. In the meantime, the descriptive map is solid enough to guide the narrative inward another step. The next section follows the microwave photons along this layered corridor, traces how evolving potentials at each depth alter their energies in small increments, and shows how the sum of those increments builds a temperature profile that can be compared directly with the cold spot's measured shape. Microwave photons that leave the last scattering surface in the early universe begin as a nearly uniform bath with small frozen imprints of primordial sound waves. On their journey to the present, they cross a landscape of evolving gravitational potentials created by the growth of large-scale structure. In a universe where expansion accelerates at late times, these potentials do not remain constant. Overdensities slowly shallow, and underdensities slowly fill in as the background stretches and the growth of structure slows. A photon that falls into a potential well gains energy, and that gain would be lost on the way out if the well remained unchanged. When the well decays, the photon loses slightly less energy than it gained and arrives a little hotter. In an underdensity, the opposite occurs. The hill that the photon climbs relaxes while it crosses, so the loss on the way up is not fully recovered on the way down, and the photon arrives a little colder. This path-dependent shift is the integrated Sachs-Wolf effect, and it operates most strongly along very long lines of sight through wide low-contrast features at redshifts where cosmic acceleration matters. The Eridanus corridor provides such a path. Its layered underdensities act like a broad sequence of shallow hills whose heights decline gently with time. A photon entering the near side loses energy as it climbs. While it traverses the interior, the background expansion reduces the contrast of the hill. The photon then descends a slightly lower slope and recovers less than it lost, leaving the corridor with a net energy deficit relative to a path through an average field. The total shift is the sum of small increments gathered across each underdense layer. The sign is cold. The amplitude depends on three elements: the depth of each layer's matter deficit, the radial width of the layer along the line of sight, and the epoch at which the crossing occurs. Layers at intermediate redshift contribute more than very nearby or very distant layers, because the rate at which potentials change is tied to the balance between matter and the component that drives acceleration. Geometry turns this one-dimensional sum into a sky pattern. The projection of a broad, nearly compensated depression produces a temperature profile with a cool center, and if compensation is present, a surrounding ring that is modestly warmer relative to the mean. That ring appears because the photon field that passes through the compensating ridge encounters a region where the potential grows slightly while being crossed, adding a small hot rim to the cold core. The observed Eridanus cold spot shows such a configuration, a deeper interior with a faint wide ring. The match in shape does not by itself certify the cause, but it is consistent with the corridor picture and with how large compensated underdensities project onto the microwave background when convolved with the instrument beam. Each layer's contribution can be expressed as an integral of the time derivative of the gravitational potential along the photon path. The potential itself is set by the matter contrast filtered on scales that match the layer's width. In the linear regime where contrasts are modest, the time derivative follows simple growth laws that depend on the cosmological parameters. The Eridanus corridor stays largely in this regime because its average contrast is moderate even if local patches are emptier. This keeps the calculation tractable and ensures that the sign of the effect remains the same across the layers. Every underdense slab adds a small cold increment. Non-linear corrections, which would matter for very deep, sharp voids, play a lesser role here. The cold profile therefore accumulates in a gentle additive fashion rather than in brief spiky steps. A lesser-known detail is that photons do not sample only the scalar potential. They also respond to weak lensing that slightly deflects their paths as they cross gradients in mass. In the Eridanus direction, the same underdense corridor that produces a small cold shift also lowers the lensing convergence, subtly reducing the amount by which small-scale microwave anisotropies are remapped. This reduction does not make the cold spot by itself, but it coheres with the corridor story. A place that is cold in projection also lenses a little less. Cross-correlating the cold spot with reconstructed lensing maps is thus a way to check that the line of sight has the expected lack of mass. Where the correlation aligns, the case for a physical corridor effect strengthens because two independent imprints, energy shift and weak deflection, agree on sign and location. The amplitude problem remains the open question. For a corridor with parameters similar to those inferred from galaxy counts and lensing reconstructions, the predicted cold decrement is typically smaller than the full depth measured at the centre of the Eridanus cold spot. This gap is not vast, but it is persistent across many reasonable profile choices. The difference invites two complementary readings. One is statistical. A random draw from the primordial field can add a baseline depression on which the corridor imprint is superimposed. The other is structural. The corridor may contain a handful of somewhat deeper subvoids, aligned fortuitously along the sightline, increasing the integrated effect beyond what a single smooth profile would predict. Current map supports some patchiness along the corridor, but the uncertainties in bias and distance keep the detailed sum uncertain. Large angles and beam smoothing also play quiet roles. The cold spot is defined after the microwave map is smoothed on degree scales to suppress small fluctuations. This smoothing blends contributions from a range of impact parameters through the corridor and softens sharp edges that a stack of idealized voids might imprint. It also ensures that any comparison between prediction and measurement must convolve the model profile with the same beam. When that is done, the corridor's calculated imprint takes a shape closer to the observed one, a broad, cold centre with a weak warming shoulder. The issue of amplitude persists after this step, but the shape alignment improves and supports the structural connection. Foregrounds are checked again at this stage because spectral behaviour matters for the integrated effect. The temperature shift from evolving potentials is frequency independent in thermodynamic units, unlike many galactic or extragalactic contaminants. Multi-frequency microwave maps cleaned with dust and radio templates show that the cold spot maintains its contrast without adopting the colour of dust or radio sources. This spectral neutrality is the expected behaviour of a genuine background feature and allows the corridor interpretation to proceed without introducing special foreground allowances. It does not select the corridor over a primordial fluctuation, but it removes foregrounds as viable alternatives to the combination of primordial plus late-time structure. A planetary scale observation remains in the backdrop. The cold spot exists within the full mosaic of large angle anomalies that include alignments of low multipoles and hemispheric power asymmetries discussed in the literature. The standard model permits such configurations by chance, but their coexistence raises interest in careful accounting. The corridor explanation does not address these broader alignments. It only offers a specific, physically motivated addition to the temperature profile in one direction. The broader anomalies are a context, not a cause, and they caution that single feature explanations should be isolated from global claims about the sky's largest modes. The corridor's internal compensation also moderates expectations. Many voids are surrounded by walls where matter that flowed outward accumulated, creating a ring that partially balances the integrated potential. In projection, compensation limits the net cold shift from the core because the warm rim contributes with opposite sign. The Eridanus corridor shows hints of partial compensation at some depths, which naturally softens the integrated signal. This is helpful for matching the observed weak warm ring, but it prevents the corridor alone from producing an extreme cold centre. A profile without compensation would overpredict the warm rim and underpredict the central depth once smoothed. The mixed-layered compensation seen in data fits better. It yields a mild ring and a deeper centre than a single compensated bowl, while still stopping short of the full measured depth, unless primordial structure adds to the base. Timing offers a final quiet check. The ISW effect peaks at redshifts where the acceleration of expansion has begun to suppress the growth of structure. The Eridanus corridor's layers sit primarily in this range. Nearby layers contribute less because potentials change slowly at very low redshift. Very distant layers contribute less because matter still dominates growth there. The placement of the corridor's main underdensities within the favoured window supports their role as contributors to the cold spot, whereas an alignment of similar width centred too near or too far would be less effective. That the corridor lies in the right epoch is therefore not decisive, but it sits on the side of consistency that a layered explanation requires. Placed together, these elements describe a steady mechanism. Photons cross a long underdense corridor during an epoch when potentials decay. Each layer adds a small cold increment. Partial compensation moderates the rim. Beam smoothing shapes the observed profile. Lensing shows a matching deficit. Spectra stay clean. Amplitude remains somewhat short of the measured centre, leaving room for a statistical low from the primordial field. The narrative remains descriptive and grounded. It neither assigns a single perfect cause nor discards the corridor as irrelevant. It holds the path open to more precise mapping of bias, better lensing reconstructions, and deeper surveys that can refine the layered profile. With the mechanism in place at the scale of line-of-sight integrals, the next step turns from the photons to the map makers. It narrows to how galaxy catalogues are converted into matter fields, with bias corrections, how masks and completeness shape the inferred corridor, and how alternative traces such as weak lensing shear and CMB lensing convergence are combined to reduce uncertainties in the Eridanus line of sight, before confronting the temperature profile again. Turning galaxy counts into a map of matter begins with a recognition that galaxies are not neutral tracers. They form more readily in overdense regions and avoid the emptiest zones. This preference is described by a bias factor that links fluctuations in galaxy number to fluctuations in underlying matter. The factor depends on galaxy type luminosity and redshift. Surveys first define clean samples with uniform selection across the sky, and then measure how the angular two-point correlation of galaxies varies with scale. By comparing this correlation with theoretical expectations for matter, a scale-dependent bias is inferred. On large scales where the fluctuations are linear and gentle, a single slowly varying bias often suffices. The Eridanus corridor is broad enough that this linear regime applies. The map makers therefore rescale galaxy deficits by the inverse of the bias to estimate the matter under density. This step introduces uncertainty, because different galaxy populations contribute at different distances, but averaging over wide redshift slices smooths the variations and keeps the conversion stable within known error bars. Completeness is the next layer. A survey that covers much of the sky does not observe every target with equal depth. Dust and stars in the Milky Way affect the ability to detect faint galaxies, and observing conditions vary between fields. To track these effects, surveys create random catalogues that mimic the angular footprint depth variations and masks imposed by bright stars and artifacts. Counts of these random points define the effective area in each pixel and redshift bin. Galaxy counts are then divided by the corresponding random counts to correct for changing completeness. This normalization prevents spurious underdensities from appearing where the survey is shallow, and prevents spurious overdensities where it is deep. In the Eridanus direction, the completeness correction matters because the corridor spans a large angle and crosses regions with different galactic conditions, After correction, the deficit persists and takes a form that matches what is expected for a physical underdensity rather than an artifact of depth. Photometric redshifts add looseness along the line of sight. Colours measured in a few broad bands yield distance estimates with uncertainties that grow for faint galaxies and for certain spectral types. The redshift error distribution is characterized by comparing a subset of galaxies with spectroscopic redshifts to their photometric estimates. This distribution is then used to deconvolve the observed counts in redshift bins, yielding a smoother estimate of the true matter profile. For a broad structure like the Eridanus corridor, this deconvolution does not sharpen the profile into a narrow void. Instead, it confirms that the underdensity extends across several adjacent bins, and that its edges are gentle. The process also tests whether a sharp, deep void could be lurking, and smoothed into a shallow trough by photometric errors. The absence of strong residuals after deconvolution argues against a single sharp cavity dominating the line of sight. Masking removes known contaminants. Bright stars create halos and diffraction spikes that mimic low galaxy counts in their vicinity. Radio sources and satellite trails create holes where no galaxies are recorded. These regions are excluded from both galaxy and random catalogues to avoid bias. The masks are apodized on the sphere to reduce artificial edges when maps are smoothed. The Eridanus field includes such masked patches, but their total area is small compared with the corridor and their distribution is not concentrated at its centre. Tests that vary the mask within reasonable bounds find that the underdensity's existence and broad shape do not depend on the exact choice, though the precise depth shifts within the quoted uncertainty. This stability is a necessary condition before linking the map to microwave features. Independent tracers help. Weak lensing shear of background galaxies offers a direct measure of projected mass-free from galaxy bias. Shapes of many faint galaxies are averaged within angular cells to detect the tiny coherent distortions caused by foreground mass. In the Eridanus direction, shear maps are noisy because the corridor is wide and low contrast, but the sign of the convergence aligns with an underdensity when averaged over the relevant scales. CMB lensing convergence provides a complementary measure at higher redshift reconstructing deflections imprinted on the microwave background itself. This reconstruction is less affected by galaxy selection and reaches smoothly across the sky. Toward Eridanus, it shows a mild deficit consistent with a supervoid corridor. Together, shear and CMB lensing confirm that the line of sight is not just deficient in galaxy numbers, but also in total mass. Cross-correlations tie these fields together. The galaxy map is correlated with the CMB temperature map to look for the expected small anti-correlation, where underdensities sit. Stacking many voids yields a weak coherent signal. Focusing on the Eridanus corridor shows an anti-correlation stronger than average but still within the tail of the distribution. Correlating the galaxy map with CMB lensing yields the expected positive relation in general and a local depression along Eridanus. Correlating weak lensing shear with the CMB temperature is more challenging due to noise, yet the sign aligns with the corridor story. These cross-checks reduce the chance that a single systematic in one dataset drives the entire inference. They also set a scale for amplitude expectations. The measured correlations suggest that part of the cold spot aligns with late-time structure, while the remainder sits in the primordial pattern. Profile modelling proceeds with care. A compensated top hat in 3 dimensions is a simple starting point, a central underdensity of constant depth and width, surrounded by a thin, overdense shell. Projected onto the sky with a finite beam, it produces a cold centre and a warm ring. The Eridanus corridor's best fits prefer smoother profiles, a central region, whose deficit rises gradually toward the centre, and edges that roll gently to the mean with partial compensation that varies by redshift. A sum of 2 or 3 such smooth components at different depths reproduces the observed galaxy and lensing profiles more naturally. When convolved with the microwave beam, the resulting temperature template aligns in shape with the cold spot. The amplitude remains lower than the measured centre by a modest fraction, signalling space for a primordial contribution. This hybrid fit is consistent with the standard cosmological model and does not require exotic physics. Systematic flaws are quantified through null tests. The same analysis is repeated after rotating the corridor to random positions with similar galactic latitude, or after shifting redshift bins to create control lines of sight. The resulting temperature profiles average to 0 within uncertainties, while the real corridor retains a cold profile. Galaxy random cross-correlations test for residual calibration patterns. These show small signals that are removed by improved weighting, after which the underdensity remains. Lensing maps are scrambled by phase randomization to assess chance alignments. The real corridor stands out at low significance, which is expected given the weakness of the signal, but the sign is consistent. Each null test constrains how much of the observed correlation could arise from survey artifacts. Together they point to a physical, if modest, contribution from the corridor. Distance ladder uncertainties enter through the conversion from angular scales and redshifts to co-moving lengths. These are set by the cosmological parameters that the same microwave background helps determine on the full sky. Using concordance values, the corridor spans hundreds of millions of light-years in depth and comparable scales in width. Varying the parameters within current uncertainties alters the predicted integrated Sachs-Wolf amplitude by small amounts compared with the gap between the corridor-only prediction and the full cold spot depth. Thus, parameter uncertainty does not erase the need for a primordial component. It instead sets the error bars on the corridor's contribution and confirms that the line of sight geometry sits in the epoch where the effect should be visible if present. Foreground residuals are bounded with frequency tests. The temperature depression's contrast is measured across multiple microwave bands and converted into thermodynamic units, where a true CMB fluctuation is frequency independent. The Eridanus profile maintains its shape and amplitude across bands after dust, and synchrotron templates are subtracted. Injecting fake dust or radio templates along the corridor shows how a hidden foreground would distort the spectrum and morphology. The observed profile does not follow these distortions. On the galaxy side, stellar contamination is estimated by cross-matching with star catalogues, and by modelling star-galaxy confusion near the galactic plane. After removal, the density deficit remains. These steps do not prove causation but reduce alternative interpretations. With these conversions, corrections and cross-checks, the matter map along Eridanus becomes a layered trough, whose bias-corrected contrast and effective width are sufficient to produce a cold imprint of the observed shape and a fraction of the observed amplitude. The remaining amplitude is compatible with a rare draw from the primordial field on large angular scales. The joint picture is conservative and testable. It survives reasonable changes in masks, bias prescriptions, photometric deconvolution and lensing reconstructions. It leaves open improvements that deeper spectroscopic coverage and finer shear maps will bring, especially by sharpening the radial profile and verifying compensation as a function of depth. The mapmaker's work closes with a loop back to the sky. The reconstructed matter corridor is projected, the predicted temperature template is convolved with the microwave beam, and the result is compared with the measured cold spot profile. Differences are framed as residuals and interpreted as the primordial component. The residual's angular shape is broad and smooth, consistent with low multipole contributions, rather than with a hidden point-like foreground. The corridor's template overlays a ring that aligns with the faint warm shoulder observed. The separate lensing deficit aligns in position. The statistics of many similar lines of sight show that this combination is uncommon, but not impossible. The standard model is not overturned. It is exercised in a demanding case, with the conversion from galaxies to matter in hand and with cross-traces consistent with an extended deficit. The narrative can proceed inward once more, now focusing on the statistical question that frames the cold spot's rarity. The next step stays calm and quantitative, weighing the probability that a primordial fluctuation of this depth appears on the smooth sky, how that probability changes when conditioned on the presence of a supervoid template, and what limits arise from stacking analyses and simulations that preserve the same survey masks and beams used in the measurements. Rarity in a random field is a statement about how often a given pattern appears when many skies are drawn from the same statistical rules. The rules for the microwave background are specified by a power spectrum that sets the variance of temperature fluctuations as a function of angular scale, and to a good approximation on large angles by the assumption that phases are random and that the field is Gaussian. In such a field, the probability of a patch with a given depth and size can be estimated by filtering simulated skies, with the same beam and mask used for the data, then counting how many patches meet or exceed the observed criteria. The cold spot in Eridanus is defined operationally by smoothing the sky on a degree scale and measuring the average temperature in circular apertures of a chosen radius. The depth of the lowest aperture mean and the shape of the profile around it are recorded. Many synthetic skies processed in the same way yield a distribution of minima. Where the observed depth lies within this distribution expressed as a percentile or as a number of standard deviations sets one measure of rarity. Masks matter because they remove parts of the sky from analysis and can bias the distribution of extrema if not accounted for. Simulations draw skies over the full sphere, apply the same galactic and point source masks as the data, and then compute aperture means only in the unmasked regions. Beams matter because smoothing reduces variance and correlates neighbouring pixels. Simulations convolve maps with the same beam before the aperture statistic is computed. When these steps are followed, the distribution of cold minima is broader than a naive full-sky no-mask, no-beam calculation would suggest. The Eridanus cold spot still falls in the tail of this distribution, but the tail is not empty. A small fraction of Gaussian skies produce minima of comparable depth once the mask and beam are included. This fraction is sensitive to the chosen aperture radius, and to whether one also demands a surrounding warm ring. If the ring is included as part of the definition, the tail thins and the cold spot's rarity increases, modestly reflecting that shape constraints add information beyond depth alone. Conditioning on the presence of a supervoid template changes the statement. Rather than asking for the probability of a cold minimum anywhere on the masked sky, the question becomes given that a particular line of sight is known to host a broad underdensity. What is the probability that the aperture mean centered on that line of sight is at least as low as observed simulations answer this by placing the aperture at the fixed position corresponding to the corridor and measuring the distribution of temperatures across many Gaussian skies drawn with the same power spectrum. The corridor contributes a deterministic, modest decrement through the integrated effect which can be added to the simulated skies as a template if one wants to test the hybrid model directly. Whether or not the template is added, the variance of the aperture mean at a fixed position is smaller than the variance of the coldest aperture anywhere, because the anywhere search benefits from a look elsewhere effect. Under this conditioning, the observed temperature sits less far into the tail than the unconditioned coldest minimum statistic would imply. The corridor thus reduces the tension between observation and expectation, not by erasing the depth, but by focusing the comparison and by adding a physical small shift with the correct sign. Stacking analyses provide a complementary population-based view. Many voids identified across a survey are aligned and their temperature profiles averaged. The mean stacked profile is small and cold at the centre, with a weak warm shoulder consistent with the integrated effect. The variance across stacks is large because individual voids live in different large-scale environments, and because the microwave background carries primordial structure that adds noise to each line of sight. The Eridanus direction can be treated as a single member of this population, but with an unusually large depth. In this view, the cold spot is a tail event among void-centered profiles, perhaps aided by a corridor that is wider than average, and by a low draw from the primordial field. The stack confirms the sign and scale of the mean imprint, and therefore supports the corridor's contribution, while the tail status accounts for the remainder as statistical fluctuation. Simulations that include both large-scale structure and the microwave field tighten this picture. Light cone realizations populate the nearby universe with halos and voids drawn from a cosmological model and project their gravitational potentials along many lines of sight. The integrated effect is computed directly from the time-varying potentials, and a Gaussian primary field with the observed power spectrum is added. The synthetic skies are then processed with the same beams masks and aperture statistics used on the data. In these joint simulations, some lines of sight that resemble the Eridanus corridor in depth and width produce cold apertures deeper than average once the primary field is added, and a few approach the observed depth. The fraction is small but non-zero. Changing the corridor's compensation, breaking it into layered components, or altering its alignment with nearby overdense structures, moves the mean imprint up or down, but does not generate extreme cold patches by corridor physics alone. The corridor acts as a bias on the distribution, not as a decisive generator of the tail. Uncertainties in the primordial power spectrum at the largest angles also enter. Cosmic variance limits how well the lowest multipoles can be known from a single sky. This uncertainty propagates into the tail probabilities for aperture minima. When simulations draw skies from a set of power spectra, sampled within the allowed range of low multipole amplitudes, the distribution of extrema broadens. The Eridanus cold spots percentile shifts accordingly, sometimes deeper into the tail, sometimes shallower, depending on the drawn low L realization. This sensitivity cautions against overinterpreting a single percentile value, and favors statements that compare classes of statistics, depth alone versus depth, plus ring unconditioned minimum versus fixed direction aperture, rather than a single number detached from its definitional choices. Foreground residuals are folded into the statistical accounting through null tests on rotated or phase-scrambled maps. Rotations preserve noise and foreground residual structures tied to the mask, while breaking any fixed alignment with the corridor. Phase scrambling preserves the power spectrum while randomizing feature placement. The distribution of aperture means from these nulls matches the distribution from Gaussian simulations, convolved with the same beam and mask, indicating that the residuals do not significantly thicken the tails. This agreement supports the use of Gaussian beam and mask-aware simulations as the baseline for rarity estimates, and reduces the chance that subtle residual foregrounds inflate the cold spot significance. The warm ring is treated in the same framework. A profile statistic measures the temperature in concentric annuli around the aperture center and fits a template with a cold core and a shallow warm shoulder. Simulations yield the distribution of best fit amplitudes for both components. The observed cold spot sits with a strong cold amplitude and a modest warm amplitude consistent with partial compensation. The joint rarity of drawing both amplitudes at the observed values is lower than the rarity of the cold amplitude alone, but not extraordinarily so when the corridor template is included. This again frames the cold spot as an unlikely but permissible outcome, within the standard rules aided by a corridor that biases the sign and shape, and by a low primordial draw that deepens the center. Conditioning can also be done in reverse select from simulations. The fraction of skies where a corridor-like underdensity lies along the same direction, in the large-scale structure realization, then ask for the distribution of aperture temperatures there. In combined structure plus CMB simulations, this conditional set shows a mean cold bias, and a tail that includes depths comparable to the observed value at low but non-negligible frequency. The result depends on how strictly corridor-like is defined effective radius, mean contrast degree of compensation, and redshift span, but across reasonable choices the qualitative outcome persists. The corridor sharpens the expectation without breaking the model's overall statistics. From a practical standpoint, these statistical layers leave a set of limits rather than a single verdict. The Eridanus cold spot is unlikely under a pure unconditioned Gaussian draw, but remains within the tails once masks, beams, and shape constraints are applied. It is less unlikely when conditioned on the existence of a broad underdensity along the sightline, and less still when a small deterministic integrated effect from that underdensity is added as a template. Stacks of voids support the sign and radial shape of the mean imprint. Combined simulations show that corridor plus primordial combinations can approach the observed depth at low frequency. None of these steps requires physics beyond the standard cosmological model. Each step also preserves the conclusion that the corridor alone modelled as a single smooth void does not reach the full amplitude. Open questions remain in the statistical framing. Different filtering choices, top-hat apertures versus compensated filters that downweight large-scale background produce slightly different rankings of tail events. The cold spot tends to remain a notable feature across these filters, but the quantitative percentile shifts. Defining the warm ring threshold is likewise subjective, and its inclusion or exclusion affects rarity claims. These dependencies are not weaknesses. They are reminders that rarity is a shorthand for a family of related operational statements. The consistent core across that family is that the cold spot is uncommon, but compatible with the model, that the Eridanus corridor likely contributes a portion of the depth, and that better maps of the corridor's radial profile together with refined low-L power estimates will tighten the conditioning further. The planetary scale observation frames the next steps. Deeper imaging surveys will reduce photometric redshift errors and sharpen the layered profile of the Eridanus underdensity. Wider weak lensing programs will lower noise in convergence maps on degree scales, clarifying compensation and confirming mass deficits independent of galaxy bias. Microwave experiments with lower noise at large angular scales and careful control of systematics will refine the cold spot's profile and its frequency independence. Simulations that couple structure growth to primary anisotropies with survey-specific masks and beams will improve conditional probabilities. With each refinement, the hybrid explanation, a rare primordial low enhanced by a broad supervoid corridor, becomes easier to test and, if correct, to quantify with narrower error bars. Having weighed rarity and conditioning within the same calm frame, the path can move one step inward again, keeping the same outer to inner discipline. The next section turns from probability to mechanics on the map itself, tracing how the compensated layered geometry of the Eridanus corridor shapes the observed cold core and warm shoulder, and how small adjustments to profile depth, width, and compensation translate into measurable differences on the smooth sky that future surveys can check directly. The geometry of an underdensity that stretches along a line of sight controls the shape of its imprint on the microwave sky after the map is smoothed. A central deficit that tapers gently toward its edges produces a cold core with broad shoulders rather than sharp rims. If a compensating ridge surrounds the deficit, the ridge adds a faint warm ring when projected. The balance between core depth and compensation sets whether the ring is obvious or only a low pedestal. In the Eridanus corridor, the profile inferred from galaxy counts and lensing reconstructions is layered, and only partly compensated, so the expectation is a prominent cold center and a weak wide shoulder that rises toward the mean rather than a bright narrow rim. Smoothing on degree scales then softens any residual edge features, blending contributions from nearby impact parameters and turning fine structure into a slow rise that matches the measured profile more closely than a single sharp bowl would. Depth, width, and compensation each leave distinct marks. Increasing the central matter deficit deepens the core of the temperature profile without greatly changing the radius where the curve turns upward, because the turn is tied mainly to the effective width of the underdensity. Increasing the width spreads the cold region on the sky and shifts the turning point outward, while leaving the peak depth less affected if compensation grows in tandem. Strengthening compensation raises the amplitude of the warm shoulder and can even overshoot the mean, but it also reduces the net cold area, because the warm annulus cancels part of the core's imprint when averaged over the smoothing aperture. The Eridanus corridor's combination moderate depth, large width, and partial compensation therefore tends naturally toward a wide, deep center with only a gentle shoulder, which is what the microwave maps show after foreground cleaning and beam convolution. Layering complicates this base picture in ways that smoothing partly hides but does not erase. A long corridor composed of several underdense slabs at different redshifts yields multiple slightly offset cold contributions that add in projection. If one slab is slightly narrower and deeper, it sets the inner curvature of the profile. If another is broader and shallower, it sets the outer rise. Compensation that varies by depth adds a low extended shoulder rather than a single ring. The sum across layers retains a cold core whose radius is set by the narrowest influential slab, while the outer slope follows the broader components. This superposition is consistent with the Eridanus reconstruction's shallow deficits over a wide span in distance with hints of deeper pockets near the centre of the line of sight. Beam smoothing and filtering determine what part of this layer geometry survives into the statistic that defines the cold spot. A degree-scale beam averages temperature over paths that pass inside and just outside the geometric edge of each slab. This averaging damps high spatial frequency features and reduces sensitivity to sharp compensation. It also pushes the observed turning radius slightly outward, relative to the true edge of the dominant slab, because off-center lines of sight contribute to the aperture mean. Compensated filters that subtract a weighted outer annulus recover some edge contrast, but the widely used top-hat apertures emphasize the interior average. In either case, the layered corridor's imprint remains broad and smooth, which is why the observed profile can be matched in shape by templates built from a few smooth compensated components, even when the exact fine structure along the sightline is uncertain. The microwave background's own large-scale modes interact with the corridor imprint through simple addition. A random primordial low that overlaps the corridor steepens the central descent and increases the apparent depth without altering the radius where the curve turns upward. A primordial high at slightly larger radius lifts the shoulder, making compensation appear stronger than the mass map alone would predict. Because the corridor template and the primordial field add linearly in thermodynamic units, one can read their relative roles from how center depth and shoulder height change together. In Eridanus, the combination of a deep center and a modest shoulder is a pattern that templates reproduce when a corridor-like underdensity is added to a mild primordial low. This is not a proof of causation, but it is a mechanical alignment between geometry and the observed profile once beam effects are included. Weak lensing adds an independent geometric check that mirrors the temperature shape at lower amplitude. The same wide, partially compensated underdensity that cools the core produces a negative convergence profile that is shallow at the center and rises gently towards zero with radius. A strong narrow compensation would create a near-zero interior and a distinct positive rim in convergence, but the available reconstructions toward Eridanus favour a broad low trough without a sharp ring. This lensing shape aligns with the temperature profile's wide core and mild shoulder, and argues against a single thin-walled void placed at a special distance. Galaxy shear maps, which are noisier on degree scales, nevertheless prefer the same sign when averaged over the corridor, reinforcing the conclusion that the temperature shape is anchored in a real deficit of projected mass. Small adjustments to the corridor geometry translate into measurable testable differences on the smooth sky. Deepening the central contrast by a modest fraction, while keeping width and compensation fixed, lowers the inner few degrees of the temperature curve almost in parallel and leaves the shoulder nearly unchanged. Widening the corridor by tens of % with the same depth flattens the inner slope and moves the shoulder outward, producing a profile that rises more slowly and risks underfitting the observed turning radius unless the beam is broader than assumed. Increasing compensation lifts the shoulder and can create a visible inflection if the annulus is narrow, but once convolved with the degree beam, the inflection softens into a more subtle upturn. These sensitivities explain why different void-finding algorithms and profile parameterizations yield slightly different best fits when projected and compared with the maps, and why families of corridor models can match the shape while differing in the split between layers. Photometric redshift errors stretch the geometry along the line of sight and favour smoother, wider reconstructions. Deconvolution that uses measured error distributions can recover sharper features if they exist, but in the Eridanus field the deconvolved profiles still prefer gentle edges and broad spans. This preference is itself a geometric statement. The line of sight seems to lack an isolated deep cavity, capable of imprinting a sharply bounded cold region, and instead hosts a sequence of mild deficits whose sum produces the wide profile. As deeper spectroscopy fills in key redshift ranges, any hidden narrow layers would stand out as local steepenings in the recovered profile. Their absence so far matches the current smooth sum that templates require. Foreground cleaning plays a quiet role by preserving geometry when done in thermodynamic units. Because the integrated effect is frequency independent in those units, a properly cleaned map removes dust and synchrotron without distorting the corridor's radial shape. If residuals remain, they typically introduce small-scale structure or large-scale gradients that do not mimic a symmetric cold core plus weak shoulder. The Eridanus maps after cleaning maintain a profile that is radially coherent and stable across frequency bands, another indication that the geometry and projection is the controlling ingredient rather than color-dependent contaminants. The cosmic web around the corridor also influences the profile through flanking overdensities. If the line of sight leaves the underdensity and enters a mildly overdense wall, the projected temperature can show a shoulder that approaches or slightly exceeds the mean at intermediate radius before returning to average at large angles. This behavior is seen in some directions that host ordinary voids with clear compensation. In the Eridanus case, the shoulder remains gentle and does not overshoot strongly, suggesting that any compensating walls are low contrast off-axis or distributed across several depths rather than concentrated into a narrow aligned ring. This inference aligns with maps that show filamentary structures brushing the line of sight rather than forming a circular wall around it. A planetary scale observation guides the interpretation of these geometric effects. The same smoothing and masking applied to the full sky reveal that wide, smooth, cold profiles with faint shoulders are not unique to Eridanus, though Eridanus sits at the deeper end of the distribution. This context is useful because it ties mechanical expectations how depth, width, and compensation project to a population of similar shapes. The corridor is an extreme example, drawn from that population strengthened by its unusual width, and by a low primordial draw, but it expresses the same map-making rules that govern milder features elsewhere. The unresolved part of the geometry lies in the precise radial weighting of layers, and in the degree of compensation at each depth. Current reconstructions produce families of acceptable profiles, whose projected shapes are nearly indistinguishable after beam smoothing. Distinguishing among them requires tighter lensing convergence maps on degree scales, and denser spectroscopic coverage to reduce redshift blur. Until then, the corridor can be described conservatively as a long, wide, partially compensated underdensity, whose projected shape explains the cold spot's curvature and shoulder, while leaving amplitude to be shared with primordial structure. The lesser-known detail is that small changes in the assumed growth rate of structure at late times within current cosmological uncertainties alter the balance between core depth and shoulder height by a measurable but modest amount. A slightly slower decay of potentials reduces the cold amplitude and lowers the shoulder. A slightly faster decay raises both with the ratio set by compensation. This sensitivity is not large enough to account for the full Eridanus depth by parameter shifts alone, but it shows why joint fits that include low multipole power lensing normalization and corridor geometry produce more stable results than any single probe. The consensus point kept steady through all of these layers is that wide underdense regions at intermediate redshift imprint small cold signals with shapes that reflect their projected geometry and compensation, and that beam-smoothed maps read these shapes directly in the form of cold cores and weak shoulders. The planetary scale observation that the sky is statistically well described by a Gaussian field with a known power spectrum remains consistent with this picture once the corridor's deterministic template is added. Within that frame, the Eridanus cold spot's shape follows from geometry. Its extra depth belongs to the tail of primordial variance. With the mechanical link between corridor geometry and the observed profile now set, the path can hold the same calm scale and move inward by one more layer, turning to how future maps can separate layered profiles with higher fidelity, deeper spectroscopy to sharpen redshift structure, lower noise lensing convergence to confirm compensation, and refined large-angle microwave measurements to tighten the balance between core and shoulder in a way that tests the corridor's detailed architecture directly. Separating a layered underdensity into its radial pieces requires maps that carry distance with finer precision and mass with lower noise while preserving the calm degree-scale view where the temperature profile is defined. The first refinement comes from spectroscopy. Photometric redshifts place galaxies along the line of sight, with uncertainties that smear features into broad troughs. Spectroscopic redshifts fix distances with much smaller errors, allowing shallow steps in density to be resolved into distinct slabs. A survey that tiles the Eridanus corridor with fibers or slits reaching from the local universe to intermediate redshift can trace how the number of galaxies and their motions change with distance. Velocity dispersions and coherent flows around void edges then add a kinematic layer to the counts, confirming where matter diverges from the centre and where any compensation gathers at the periphery. When these slices are stacked, the corridor's width in co-moving units becomes a measured profile rather than an inference, and the relative weight of each slab is established with errors dominated by shot noise rather than by distance blur. Weak lensing convergence maps supply the second refinement. Shapes of many faint background galaxies averaged over large cells reveal the tiny shear imprinted by foreground mass. The challenge in the Eridanus direction is not confusion by small-scale structure, but the need to keep noise low over degree scales where signals are weak and smooth. Deeper imaging with stable, well-characterized point spread functions reduces shape noise and allows a cleaner reconstruction of convergence across the corridor. Tomographic slicing of source galaxies by redshift then separates the lensing signal into broad foreground layers, tying mass deficits to the same distances that spectroscopy delineates. The result is a projected matter field that shows a negative trough without relying on galaxy bias, and that can be integrated with the same radial weights used to predict the microwave imprint. Where compensation exists, the convergence approaches zero gently at the edges rather than spiking into a narrow rim, and this trend can be tested as depth increases. The microwave background maps themselves form the third refinement. Large-angle measurements need careful control of bandpass side lobes and foreground subtraction to avoid gently varying artifacts that can stir degree-scale profiles. Multi-frequency instruments reduce this risk by separating emission with different spectral behavior before smoothing. When temperature maps from several bands agree in thermodynamic units after cleaning, the remaining profile can be treated as part of the background rather than a foreground residue. Polarization measured on the same large scales plays a quiet supporting role. While the integrated energy shift that underdensities produce is a temperature effect, polarized galactic emission is a major contaminant that is removed more reliably when its spatial structure is mapped directly. Cleaner polarization maps lead to cleaner foreground templates, and indirectly to more stable temperature profiles in regions like Eridanus, where dust gradients are present but modest. Combining these elements turns the corridor from a descriptive sketch into a constrained model. A spectroscopic catalogue defines radial bins, whose widths reflect the intrinsic smoothness of the density field rather than photometric uncertainty. A lensing convergence map sliced tomographically assigns a mass contrast to each bin, independent of how galaxies populate the web. A microwave template built from the time derivative of the potential along the line of sight and convolved with the instrument beam predicts a temperature profile that can be compared directly with the measured curve. Residuals are then interpreted as the primordial component that shares the aperture with the corridor imprint. Because each ingredient carries its own noise, the comparison proceeds with a joint fit that treats mass bias compensation and growth history consistently. In such fits, the ratio of core depth to shoulder height becomes a sensitive indicator of compensation and of the radial weighting among layers, while the absolute depth reflects both the corridor and the low draw from the primordial field. A lesser-known detail strengthens this program voids and supervoids imprint not only temperature shifts, but also subtle correlations between temperature and the large-scale E-mode polarization pattern of the microwave background through the same late-time potential decay. The effect is small, yet along a long, underdense corridor it adds a gentle, scale-dependent cross-signal that can be sought once polarization maps reach lower noise on large angles. Detecting such a correlation in the Eridanus direction would not raise the cold amplitude, but it would add an independent frequency clean confirmation that the temperature depression includes a late-time component tied to evolving structure, rather than being purely primordial. The corridor's geometry can also be tested with galaxy colours and star formation indicators that respond to environment. Within underdense regions, galaxies often show higher fractions of late types, and bluer colours relative to denser filaments. A gradient in these properties along the sightline measured in spectroscopic slices would be consistent with an extended low-density path. Such environmental signals do not replace mass maps, but they support the picture that the corridor is real in 3 dimensions and not a chance artifact of selection. Where a compensating wall exists, an uptick in quenched fractions and velocity dispersions may mark its presence, providing another indirect measure of compensation that can be compared with lensing and counts. Statistical framing improves as these maps refine. Conditional probabilities that now rely on templates with broad uncertainties can be rerun with measured profiles and tighter beams. The look elsewhere adjustment shrinks naturally when the question remains tied to a fixed line of sight, whose mass, width, and compensation are known. Stacked analyses can split voids by compensation strength, or by width to check whether the Eridanus shape sits where a corridor of its measured type should sit rather than at the extremes of a mixed population. Simulations that couple structure growth to the microwave field can then reproduce the corridor with its actual depth and width, rather than with a family of plausible models, and measure how often the combined draw reaches the observed center depth once the primordial field is added. Foreground control remains part of every step. Spectroscopic targeting must avoid biases tied to stellar density and dust that vary across galactic latitude. Lensing reconstructions must track and remove additive shear from the instrument and the atmosphere, and calibrate multiplicative biases in shape measurement that grow with source faintness. Microwave maps must guard against bandpass mismatch and temperature to polarization leakage that can tilt large-scale baselines. Each of these controls is routine in deep surveys, yet the Eridanus corridor's size means that small, smooth systematics matter more than in studies of compact structures. Null tests, rotations, phase, scrambles, jackknives remain essential even as data quality improves, because the tail status of the cold spot means that rare combinations of noise and structure can still masquerade as causation if checks are lax. Planetary scale context persists through these refinements. The microwave background remains a single sky, where the largest modes are subject to cosmic variance. Improvements shrink instrumental noise and foreground residuals, but do not eliminate statistical limits intrinsic to observing one realization. The Eridanus cold spot's depth, when framed within this context, will always carry an irreducible uncertainty about how unusual it is among possible skies. The role of the corridor is less constrained by this limit because it is mapped in 3 dimensions with independent tracers. As those maps sharpen, the fraction of the profile attributable to evolving structure can be bounded more narrowly, leaving a cleaner residual for the primordial field that defines the final depth. An unresolved question guides the quiet end of this step: how finely must compensation be measured to fix the shoulder's height, with the precision needed to split causes? Compensation's contribution is small after smoothing, but it sets the gentle rise surrounding the core. If a narrow off-axis wall exists at some depth, it could lift the shoulder slightly without forming a sharp ring after beam convolution. Distinguishing such a wall from a broad, shallow compensation spread across several layers requires tomographic lensing with noise floors low enough to resolve degree scale convergence at multiple redshifts. This requirement ties the answer to future surveys with wide area deep imaging and precise photometric calibration. The mechanical link between growth history and imprint supplies another lever. The time derivative of the potential peaks at intermediate redshift. Small adjustments to the measured growth rate of structure at these epochs change the predicted cold amplitude for a fixed mass profile. Joint fits that include redshift space distortions from spectroscopy and lensing normalization thus refine not only the corridor's geometry, but also the late-time growth that mediates the temperature shift. In this way, the Eridanus direction becomes a gentle independent cross-check on the consistency between large-scale structure and the microwave background at large angles, without relying on any single statistic. In practice, the pathway for testing is straightforward. A deep spectroscopic program tiles the corridor, producing layered density and velocity fields. A wide, low-noise, weak lensing survey reconstructs convergence and shear across the same footprint and slices sources into redshift bins that bracket the corridor. A multi-frequency microwave experiment provides large-angle temperature maps with stable baselines and clean foreground removal and polarization maps that help guarantee the cleaning. Templates built from the measured mass profile are convolved with the beam and compared in shape to the temperature profile. The difference in amplitude is assigned to the primordial field. Simulations that mirror the survey masks and beams, and that include the measured corridor and the structure, yield conditional probabilities that replace earlier broader estimates. Each step narrows uncertainties without changing the calm conclusion that an extended underdensity can account for part of the cold spot, while the remainder belongs to the random large-angle background. Nothing in this refinement alters the larger sky. The cold spot remains a wide, coherent depression with a mild shoulder after cleaning. The Eridanus line of sight remains less crowded than average across a long path. The standard cosmological model continues to predict a small cold imprint from such a corridor. What changes is the precision with which depth, width, and compensation are mapped, and the stability with which the corridor's contribution is separated from the primordial remainder. The result is a clearer partition of causes that can be stated without speculation. An underdensity measured in 3 dimensions, and in mass contributes a deterministic small temperature decrement with a shape that matches the observed profile. The extra depth is a rare but allowed draw from the large-angle background. With these practical and conceptual refinements in place, the path can move inward one step further, while staying on the same gentle slope. The next section keeps the focus on observables and turns to the integrated analysis itself, where joint fits to spectroscopy lensing and microwave temperature extract the corridor's fraction propagate errors coherently and present a final survey-driven partition between late-time structure and primordial variance for the Eridanus cold spot. A joint analysis that partitions the Eridanus cold spot into late-time structure and primordial variance begins with a forward model that predicts from measurable fields the temperature profile seen after smoothing and masking. The ingredients are a 3-dimensional matter. Contrast along the line of sight, a growth history that sets how gravitational potentials decay, a beam that blurs structure on the sky, and a mask that removes foreground bright regions. The matter contrast comes from bias-corrected galaxy counts, anchored by spectroscopy, and from weak lensing convergence sliced tomographically. The growth history is described by parameters that also enter large-scale structure, fits elsewhere, so the model ties those to priors consistent with independent surveys. The beam is measured from planet scans or compact sources. The mask is fixed by the same criteria used to clean the temperature maps. With these pieces in place, the analysis predicts a deterministic temperature template from the corridor by integrating the time derivative of the potential across distance, projecting onto the sky and convolving with the beam. This template is then compared with the observed temperature profile in the Eridanus direction. The difference is attributed to the primordial field, which is modelled as a Gaussian random process, with a covariance given by the large angle power spectrum after masking and smoothing. The comparison proceeds through a likelihood that evaluates how well the sum of the corridor template and a realization of the primordial background matches the measured profile. Because the background is random, but its statistics are known, the likelihood integrates over all background realizations compatible with the observed covariance. Practically, this is implemented by writing the data vector as the set of temperature averages in concentric annuli centered on Eridanus, and by forming their covariance matrix from masked beam-convolved simulations that share the measured power spectrum. The model vector is the corridor template evaluated in the same annuli. A single amplitude parameter multiplies the template to absorb residual uncertainties in bias compensation and growth normalization. Its prior is centered on unity, with a width derived from the combined errors in the mass and lensing reconstructions. Nuisance parameters allow for small baseline tilts that capture any residual large-scale gradients left by foreground cleaning, constrained by null regions near the corridor. The likelihood then yields a posterior for the template amplitude, and for the residual primordial component with uncertainties propagated coherently. Spectroscopy enters by fixing the radial weights of the corridor. The joint fit uses redshift bins set by the measured smoothness of the galaxy field, and by the resolution of the tomographic lensing slices. Within each bin, the bias-corrected galaxy contrast and the lensing convergence provide two estimates of mass deficit that the model combines with a noise-weighted average, allowing for a modest offset that accounts for scale-dependent bias. The growth factor's time derivative is evaluated at each bin's effective redshift with priors that reflect constraints from redshift space distortions and from the overall normalization of lensing. The integrated potential change along the corridor is then the sum across bins of these weighted deficits multiplied by the growth term projected onto the sky through the angular kernel that maps a comoving radius to an annular radius and finally smoothed with the beam. The resulting template has a cold core and a weak shoulder, whose exact curvature carries the imprint of the measured compensation as a function of depth. The covariance of the annular averages is not diagonal. Large angle modes of the primordial background correlate neighbouring annuli even after smoothing. The mask further mixes modes and introduces off-diagonal terms. To capture this structure, the analysis generates Monte Carlo skies. With the measured power spectrum applies the same mask and beam and computes annular averages for each realization, building an empirical covariance that stabilizes the inverse needed for the likelihood. This covariance is then regularized with a shrinkage estimator that blends the empirical matrix with a smooth analytic approximation to avoid noise amplification in inversion. Cross-checks confirm that the resulting inverse covariance yields unbiased parameter recovery when injected. Templates are recovered from mock data. In this way, the primordial variance that remains after subtracting the corridor template is handled statistically rather than fitted explicitly, preserving the calm logic that the background is a random field with known statistics. Model comparison follows. A baseline model contains the corridor template plus a free primordial residual. A null model contains only the primordial residual. A more flexible model adds freedom to the corridor's compensation by allowing the shoulder height to vary independently within limits set by lensing. Bayesian evidence ratios between these models quantify how strongly the data prefer inclusion of the corridor template. Because the corridor template's shape is fixed by independent measurements, the penalty for extra parameters is small, and even a modest improvement in fit across the inner degrees of the profile can yield a meaningful preference. In tests on control directions where no supervoid is present, the evidence does not favour a template showing that the method does not spuriously prefer structure. In the Eridanus direction, the evidence rises for the baseline model over the null, with the strength depending on how tightly the priors on bias and growth are set. This preference is not extreme, but it's stable under changes in mask apodization beam width, within uncertainties and annulus definitions. Error propagation is explicit. Uncertainties in bias are propagated by sampling bias models consistent with the galaxy 2-point function and with environmental trends along the corridor. Each sample produces a modified mass profile and thus a slightly different template. Uncertainties in lensing normalization are sampled from shear calibration priors and from CMB lensing amplitude constraints. These shift the template amplitude and shoulder while keeping shape nearly fixed. Photometric redshift scatter affects the mapping from spectroscopy to full depth. This is propagated by convolving the spectroscopic profile with the measured error kernel and sampling its width. Each draw yields a template realization. The ensemble feeds the likelihood so that posterior uncertainties include profile uncertainty as well as primordial variance. In the final posterior for the template amplitude, the width often reflects both sources and the mean sites close to, but not exactly at unity, indicating that the independently constructed corridor slightly under or over-predicts the cold depth within the combined error budget. The joint fit returns three numbers of interest. The first is the best fit corridor amplitude and its uncertainty, which quantifies the deterministic fraction of the cold spot. The second is the residual depth at the center, attributed to the primordial field with an uncertainty that reflects cosmic variance and fitting noise. The third is a correlation coefficient between the data and the template, which measures how much of the profile shape is aligned with the corridor independent of amplitude. In typical outcomes with current data, the amplitude is of order, one with an uncertainty that admits modest departures. The residual depth is significant, but smaller than the full depression, and the correlation is positive and non-trivial, consistent with a real shape match. These numbers translate into a statement that a measured fraction of the cold spot is explained by late-time structure with quantified error bars, while the remainder is consistent with a low draw from the primordial background, given the covariance under the mask and beam. Null tests accompany the fit. Rotating the template to random longitudes at similar galactic latitude and refitting yields amplitudes centered near zero with widths that match the predicted noise. This guards against overfitting masked gradients. Replacing the Eridanus mass profile with profiles from other equally wide corridors and repeating the analysis yields a distribution of amplitudes whose mean and spread agree with stacking expectations. This checks that the method is not tuned to a single direction. Injecting synthetic templates into simulations and recovering their amplitudes tests linearity and bias. The analysis passes these tests within tolerances set by the number of simulations and by mask complexity, lending confidence that the partition in Eridanus is not an artifact of the pipeline. A lesser-known refinement adds large-angle polarization as a safeguard against foreground leakage. While the corridor-induced temperature template is frequency-independent in thermodynamic units, residual dust leakage could tilt baselines and distort the annular averages. Fitting and subtracting a small component correlated with the dust polarization intensity map reduces this risk without removing genuine background structure, because the correlation coefficient between the cold spot profile and dust polarization is low after cleaning. Including this subtraction in the pipeline shifts the baseline nuisance parameter, rather than the corridor amplitude, supporting the view that the shape match to the template is not driven by foregrounds. The outcome remains conservative. Even with improved spectroscopy and lensing, the corridor contribution's uncertainty is set not only by measurement errors, but also by the intrinsic covariance of the large-angle background under the mask. The posterior therefore has finite width that cannot be shrunk by local data alone. That width is the quantitative expression of cosmic variance. It frames the final partition as a range. The late-time corridor accounts for a measured fraction with error bars. The remainder is assigned to the primordial field with error bars of comparable size. The statement is precise without overreach. No single cause dominates, and no exotic mechanism is required. Future data narrow these ranges. A denser spectroscopic grid reduces radial profile uncertainty. Lower noise degree-scale lensing maps tighten compensation and shoulder predictions. Wider multi-frequency microwave maps stabilize large-angle baselines further and reconfirm frequency independence. With each gain, the corridor amplitude posterior tightens, and the residual contracts accordingly. The Bayesian evidence in favor of including the template grows as shape uncertainty falls. If a small scale-dependent cross-correlation between temperature and large-angle E-mode polarization along the corridor is detected, the late-time component gains an additional independent anchor, further separating it from the primordial remainder. Placed back into the calm narrative, the integrated analysis supplies the quantitative partition that the earlier descriptive sections foreshadowed. A wide-layered, partially compensated underdensity measured in 3 dimensions, and in mass produces a deterministic cold template, whose shape matches the Eridanus profile, and whose amplitude explains a portion of the depth. The remaining depth is a tale of the primordial background once masks, beams, and covariances are properly included. The division carries explicit uncertainties and passes null tests designed to expose bias. Nothing in this process changes the broader sky. It sharpens one corridor's share and leaves the rest to the random fabric of the early universe. With the joint fit complete and the partition stated one final step can widen the view slightly to close the path, a quiet summary of how the corridor result fits alongside other large-angle anomalies, how improved surveys may change only the widths of the error bars rather than the central picture, and how the Eridanus cold spot read through this lens remains a calm meeting point of late-time structure and primordial variance. Large-angle structure on the microwave sky contains more than one curiosity. Alongside the Eridanus cold spot alignments among the lowest multipoles and hemispheric differences in power have been discussed for years. Each feature is defined by an operational filter applied to a single sky. Each sits in the tail of a distribution drawn from the same statistical rules, and each carries uncertainties enlarged by masks and beams. The Eridanus corridor enters this landscape as a case where late-time structure plausibly adds a small deterministic imprint that is measured and then subtracted in a joint fit, leaving a residual that belongs to the primordial background. The broader anomalies do not change this conclusion. They set the stage into which the corridor's contribution is placed. The cold spot remains unusual, but compatible once conditioning and templates are applied. The alignments and hemispheric differences are noted at the same time as features that inform caution in rarity claims, but do not require changes to the mechanical link between an underdense corridor and a cold core with a weak shoulder. Future surveys alter the firmness of the numbers rather than the shape of the story. Deeper spectroscopy in the Eridanus direction reduces the uncertainty in the radial profile by turning broad photometric slices into thinner layers with measured velocities and cleaner edges. The corridor's width becomes a measured length in co-moving units. Partial compensation becomes a mapped rise rather than an inferred shoulder. Low-noise weak lensing programs add tomographic convergence with degree-scale fidelity, bringing the projected mass deficit into focus without reliance on galaxy bias, and confirming that edges rise gently rather than spike into narrow rings. Multi-frequency microwave instruments continue to lower noise on large angles and stabilize baselines, keeping the temperature profile clean and frequency independent in thermodynamic units after foreground removal. Together, these improvements tighten the corridor template and compress the likelihood's uncertainty on the deterministic fraction, but they do not change the qualitative partition, a measured share from late-time structure and a residual from the primordial field. Simulations track these gains by mirroring the exact masks, beams, and survey completeness of the data. They draw many skies from the same large-angle power spectrum imprint measured corridors into the structure fields and recompute conditional probabilities that the residual reaches the observed depth. As inputs sharpen, tail estimates narrow. The cold spot's percentile relative to conditioned skies becomes a number with smaller error bars. The corridor template's amplitude posterior centers more tightly around unity if the mass profile is correct. Evidence ratios comparing models with and without the template grow in favor of inclusion. None of these shifts alters the calm reading of causation. They simply move uncertainty from broad overlapping bands into thinner ones that are easier to state and to compare across studies. Other large-angle features continue to be weighed in parallel. Alignments among low multipoles remain a subject for full sky analyses that extend beyond one corridor. Their interpretation is limited by cosmic variance, and improved control of foregrounds and beams stabilizes their statistics without eliminating the intrinsic scatter that comes from measuring one sky. Hemispheric power asymmetries likewise persist or fade as definitions are tuned. The connection between these features and the Eridanus cold spot is contextual rather than causal. They remind the analysis that single numbers like percentiles depend on filters, masks, and beams, and they encourage the practice adopted here frame rarity in families of related statistics, condition on external information when appropriate, and use templates grounded in independent data to remove deterministic components. In this way, the cold spot is not isolated, but sits properly within the field's larger discussion of tails and tests. The corridor result also fits alongside stacked measurements of voids and clusters. Stacks continue to confirm that void centers are slightly cold and cluster centers slightly hot, with amplitudes that match late-time potential decay when profiles are measured and beams are applied. The Eridanus direction sits at the cold end of the void-centered distribution, while sharing its overall shape. As stacks split by width, and compensation corridors most like Eridanus in measured parameters show stronger average cold cores and slightly higher shoulders than narrower or more strongly compensated examples. This stratification increases confidence that the template built from the Eridanus mass map has the correct curvature, and that the residual depth is not the product of a mismatched shape. It also makes clear that corridors alone do not generate deep isolated depressions after smoothing. They bias outcomes that are completed by the random large-angle background. A planetary scale observation returns throughout these comparisons the largest modes on the sky are few in number, and their amplitudes fluctuate between realizations even when the power spectrum is fixed. This intrinsic scatter is the reason the residual in Eridanus cannot be determined to arbitrary precision. The covariance of annular averages under the mask retains off-diagonal structure that no additional local measurement can remove. The corridor's template, in contrast, can sharpen as mass maps improve because it is anchored in three-dimensional observations that are not limited by the same cosmic variance on large microwave angles. The asymmetric future therefore favours tighter bounds on the deterministic share and persistent finite width for the primordial remainder. Ancillary tracers can offer quiet cross-checks without altering the partition. Tomographic Sunyaev-Zeldovich maps, which record pressure along the line of sight, should show little or no excess in the corridor if it is underdense and lacks massive halos at the relevant depths. Radio galaxy counts should be modestly depressed if those sources trace mass on large scales. Integrated starlight from deep imaging may show a slight deficit in diffuse light associated with galaxy outskirts. Each of these checks helps guard against a hidden overdense wall or an unmodelled foreground that would otherwise disturb the interpretation. Where they align with the lensing and spectroscopic maps, they buttress the corridor's measured geometry, and by extension the shape of the template used in the joint fit. At the conceptual edge, the corridor analysis illustrates how late-time structure and primordial variance can be separated on the same angular scales without invoking speculative physics. The template arises from underdensities whose existence is measured in 3 dimensions. The residual arises from degrees of freedom laid down at early times and read through the large-angle covariance of the masked sky. The two pieces add linearly in thermodynamic units and are handled with coherent error propagation. The method therefore provides a practical path for other corridors and other features where late-time templates can be built. It does not rely on special pleading for one direction. It operates by the same rules that govern cross-correlations between large-scale structure and the microwave background, more generally now focused with care on one line of sight, where conditioning is especially relevant. The limits are clear and untroubling. A corridor cannot in this model produce the entire cold spot depth on its own, once compensation and beam smoothing are included. A primordial residual cannot be reduced to an exact number because of cosmic variance under the mask. Foregrounds, when cleaned with multi-frequency data and constrained by polarization, do not mimic the measured frequency-independent profile. Within these limits, the measured partition is stable. A wide-layered, partially compensated underdensity contributes a deterministic cold core of known shape and measured amplitude. A residual centered depression remains that is consistent with a low draw from the large-angle background. As instruments improve, the corridor share tightens and the residual's error bars shrink but do not vanish. Returning to the outer to inner structure that guides this account, the narrative has moved from the full smooth sky and its largest modes to a single corridor where geometry shapes a profile through measurements that turn galaxy counts into mass, and mass into a temperature template down to a joint fit that separates late time imprint from primordial variance. The result is quiet and sufficient. It preserves the standard cosmological model exercises it in a demanding direction, and yields numbers that can be checked with future maps. It places the Eridanus cold spot neither as a singular challenge nor as a trivial fluctuation, but as a meeting point where a measured underdensity and the random fabric of the early universe share one aperture in proportions that data now constrain. With this balance stated, the path can narrow once more to close the sequence in the same steady voice. The remaining step returns to observables on the sky, distills the corridor share, and the primordial remainder into a final survey-driven description of the Eridanus profile, and settles into the calm that follows measurement: a cold core with a weak shoulder, a dark that is statistical rather than absolute, and a line of sight through a wide underdensity that quietly lowers the temperature of ancient light. On the sky, the Eridanus direction presents a profile that observers can measure with a small set of operations that keep the view stable and reproducible. A temperature map in thermodynamic units is cleaned of foregrounds by combining many frequency bands, each of which responds differently to galactic dust and synchrotron emission. The cleaned map is then smoothed with a beam that is a few degrees across. A circle is placed on the Eridanus coordinates, and average temperatures are computed in concentric annuli from the centre outward. The result is a curve that begins cold rises smoothly and approaches the mean with a faint broad shoulder. This same curve is computed for rotated control positions at similar galactic latitude to check for Musk bias. The Eridanus curve remains distinct among those controls. It sits below the mean by an amount that is small in absolute units, but large relative to other directions when filtered and smoothed in the same way. The shape is coherent. There is no sharp edge. There is no narrow rim. The curve expresses geometry and projection, and the smoothing that observers apply to reduce noise and residuals. A mass map for the same direction is built with a parallel discipline. Galaxy surveys provide counts as a function of angle and estimated distance. The counts are divided by a randomized catalogue that carries the survey footprint and depth, which removes gradients from coverage and seeing. Bias corrections link galaxy fluctuations to matter fluctuations on large scales. Wide redshift slices minimize the impact of distance errors and highlight structures whose size matches degree scales on the sky. Lensing maps of convergence and shear from both background galaxies and the microwave background add a direct measure of projected mass that does not rely on how galaxies populate the web. When these fields are co-added in the Eridanus direction, the result is a trough that is gentle in depth and wide in angle with edges that rise to the mean gradually rather than sharply. The lensing trough is weaker than the temperature depression because it measures mass directly, but it traces the same footprint after smoothing. The mass maps therefore agree with the temperature map on sign and on width, which is the basic consistency that any corridor explanation must supply. From these two elements, a template is constructed. The measured matter deficit is converted to a potential that evolves with time under a chosen background cosmology. The time derivative is integrated along the sightline to predict a small negative temperature shift that is then convolved with the same beam used on the data. The template shows a cold core and a weak shoulder, with the ratio of core depth to shoulder height set by the degree of compensation measured in the mass mapping. This template is not tuned to match the temperature curve's depth. Its amplitude is fixed up to an uncertainty estimated from bias and lensing calibration. The template is then compared with the observed annular profile by subtraction. The residual is the part that the corridor cannot account for. Its shape is smooth and broad, consistent with the low, multipole structure of the primordial background, rather than with a localized foreground. The residual's amplitude is smaller than the full depression and larger than zero, which is the statement that a portion of the cold spot belongs to the random large-angle field, even when the corridor is accounted for conservatively. The same method is checked with nulls. Templates from unrelated wide underdensities are rotated into the Eridanus position and subtracted. Their residuals do not improve the fit. Synthetic corridors with strong narrow compensation are projected and subtracted. They create shoulders that overshoot the measured profile after beam smoothing. Templates that ignore lensing normalization underpredict the shoulder. Each null test returns to the same outcome. The Eridanus corridor template, built from the measured mass deficit with partial compensation and wide extent, aligns best in shape with the data. The remainder then sits naturally with the primordial field constrained by the covariance of large angles under the mask. The corridor's fraction is stated with error bars that are set by three sources. The first is measurement uncertainty in the mass map, which includes shot noise in spectroscopy, photometric scatter in redshifts, and shape noise in lensing. The second is modelling uncertainty and bias, and in the growth rate of structure at late time, which changes the amplitude of the integrated effect while leaving its shape largely fixed. The third is cosmic variance in the primordial background under the mask, which correlates the annular averages even after smoothing and sets a floor to how precisely the residual amplitude can be known from one sky. The first two shrink as surveys improve. The third does not. The resulting partition is therefore a range, a measured share from the corridor, a measured share from the primordial field, and covariances that express how those shares trade as templates and data are varied within their allowed limits. A lesser-known detail appears in polarization and in environmental traces. Along a long, underdense path, the cross-correlation between large-angle temperature and E-mode polarization receives a tiny contribution from the same decaying potentials that shift photon energies. The signal is small and currently below practical detection in a single corridor, yet its sign and scale are fixed by the same physics that builds the temperature template. Its eventual detection would be a frequency-clean confirmation that late-time structure contributes. In the galaxy field, the fraction of late-type galaxies often increases inside underdensities. Mild gradients in colour and star formation indicators along the Eridanus slices are therefore expected, and are found at a level that supports a real extended low-density path without replacing mass mapping. These side measurements add quiet consistency without changing the main partition. An unresolved point remains in the exact degree of compensation as a function of distance. Compensation is the rise in density around a void that balances mass conservation when material flows outward from the centre. In the Eridanus corridor, compensation appears weak and spread across many depths. A narrow, strong ring would raise the shoulder above the mean even after smoothing. The observed shoulder is gentle, which favours partial layered compensation. Tomographic lensing with lower noise on degree scales is the tool that can measure this distribution more cleanly. Until that arrives, the corridor template uses priors for compensation taken from the joint mass maps, and produces a shoulder that matches the observed rise in amplitude but carries extra uncertainty in width. This uncertainty is already small compared with the uncertainty in the primordial residual under the mask. A planetary scale observation frames the entire exercise. The largest modes on the microwave sky are few in number. Their phases are random under the model and cannot be fixed by more data from the same sky. This limitation sets the irreducible width of the residuals posterior in the Eridanus partition. It is not a flaw of the method. It is the limit of what a single realization can offer on these angles. The corridor, in contrast, is mapped in 3 dimensions, with many lines of sight and many galaxies, and with lensing of many faint sources. Its uncertainty is therefore technical rather than fundamental, and will shrink as surveys deepen. The asymmetry is useful, the deterministic share tightens, the random share remains honest about its flaw, and the joint statement stays stable and testable as new maps appear. Placed back into a single paragraph, the observables align in a calm chain. A cleaned, smooth temperature map shows a broad, cold centre, with a weak shoulder toward Eridanus. A mass map assembled from bias-corrected counts and from lensing shows a wide, partially compensated underdensity along the same line of sight. A template built from this underdensity and convolved with the same beam reproduces the observed profile's curvature and shoulder, and explains a measured fraction of the depth. The residual is smooth frequency, independent and consistent with low, multipole structure of the primordial background under the same mask. Null tests do not overturn this partition. The error bars include measurement noise modelling, uncertainty, and the cosmic variance flaw that no local observation can erase. Together, these ingredients complete the outer to inner path for this feature without departing from the standard model or from the discipline of matched beams masks and covariances. The scene then settles in scale. Far from the Eridanus direction, the microwave sky remains a near uniform field of ancient light, with small coherent undulations. Toward Eridanus, one such undulation is a little deeper than average after smoothing. The nearby universe along that path is a little emptier than usual across a long distance, and potentials there decay in a way that nudges photons toward lower energy by a small deterministic amount. The rest of the depth belongs to the random arrangement of large-angle modes laid down long ago. No special surfaces required, no new forces needed. The corridor is wide, the shoulder is mild, and the cold core is partly structural and partly statistical. Future surveys will narrow the corridor's fraction by mapping compensation and width with better fidelity. The residual will remain present with a width set by the single sky. The profile on the sky will stay the same, a cold centre that rises toward the mean, smooth and broad, marked by the same beam and the same mask. With this final observable's first account complete, the narrative returns to quiet. The cold spot in Eridanus is a meeting line between late-time structure that is measured in 3 dimensions and a primordial background that carries large angle variance. The partition between them can be stated with numbers and with uncertainties that match the methods used. The sky remains consistent with the model that predicts both parts. The corridor remains a real extended underdensity that adds a small deterministic imprint. The remainder remains a fair draw from the early field. The map, the mass, and the measure agree on these points, and the calm that follows is the calm of a problem placed within known limits, and read with matched tools. Alternative explanations for the Eridanus cold spot have been proposed, yet each must pass the same filters that the corridor model passes: frequency independence in thermodynamic units, stability under masks and beams, and agreement with independent traces of mass along the line of sight. One class suggests that the cold spot could be a pure statistical low, drawn from the primordial background without help from late-time structure. This proposal is consistent with the rules of a Gaussian field, and it gains weight from the fact that a small fraction of simulated skies do produce depressions of similar depth when smoothed and masked in the same way. However, when the measured underdensity along Eridanus is taken into account, the argument shifts from only primordial to primordial plus measured corridor, because ignoring a real mass deficit that contributes with the correct sign would leave an unnecessary mismatch between map and structure. The hybrid description therefore remains the conservative baseline, a rare draw that is made slightly deeper by a long-layered underdensity whose imprint can be computed and compared directly with the profile on the sky. Another class invokes exotic imprints, such as a relic of an early-time defect that could leave a localized temperature feature with a characteristic profile. These ideas are framed to respect frequency independence and to survive masking, yet they face constraints from the absence of correlated signatures elsewhere, and from the success of the standard model in matching the full power spectrum and polarization patterns. Any additional imprint must be rare, local and subtle enough not to disturb those matches while reproducing the exact curvature and weak shoulder observed after beam smoothing. The Eridanus corridor in contrast requires no new physics, and its template follows from measured mass. The presence of a real underdensity with the right geometry and depth argues that the deterministic part of the profile is explained more naturally by late-time structure than by a special early-time event that leaves no other clear traces. Systematic errors form a third class of alternatives. Foreground residuals in temperature could carve smooth depressions if dust gradients or radio source masks align by chance, and photometric artifacts could impose false troughs in galaxy counts that masquerade as mass deficits. The checks already applied are tuned to these risks. Multi-frequency cleaning and crossband agreement remove foreground color as an explanation. Rotations and phase scrambles test whether mask-bound structures inflate tails in temperature statistics. Random catalogues, depth maps and star density templates test whether galaxy counts track observing conditions rather than structure. Lensing convergence from background galaxies and from the microwave background supplies an independent mass map that does not know how galaxies were selected. The consistency across these fields in the Eridanus direction does not leave room for a single systematic to drive both temperature and mass signals with the required alignment and scale. Residual systematics remain as noise flaws that thicken error bars, not as coherent features that replicate the observed frequency-independent cold core with a mild shoulder. Within the late-time structure explanation itself, uncertainties persist in detail rather than in sign. The radial weighting among layers is not uniquely known, because photometric redshifts blur distance, and because spectroscopy still thins at some depths. Compensation is measured with error, especially where lensing noise grows on degree scales. Bias conversion from galaxy counts to matter carries scale and type dependence that is averaged, but not erased in broad bins. These uncertainties are handled by priors and by ensembles in joint fits, and they appear as width in the posterior for the corridor amplitude. They do not invert the sign of the imprint or erase the shape match between the template and the data. They tune how much of the core depth belongs to the deterministic share and how much remains in the primordial remainder. The lesser-known detail in this accounting is that the same corridor that cools the core should also slightly reduce the lensing of small-scale microwave anisotropies through a local dip in convergence. This effect is tiny, yet it runs in parallel with the temperature imprint and is frequency-independent. Reconstructions suggest a mild deficit consistent with this expectation toward Eridanus. Its presence is not decisive because noise is high at these scales, but its agreement in sign and footprint adds another independent piece to the geometric picture without changing any large conclusions. An unresolved question is how precisely the compensation is distributed in angle and in depth. A narrow ring placed exactly at the right redshift would create a stronger shoulder than is observed after smoothing and could alter conditioned probabilities by a small amount. Current maps favour a gentle layered rise rather than a sharp rim which supports the measured shoulder height and keeps the hybrid partition stable. Tomographic convergence with lower noise will test this directly by slicing the corridor into broader, cleaner layers and by measuring whether any single depth hosts a wall strong enough to lift the shoulder above the mean. Until then, the uncertainty sits in widths and amplitudes of the shoulder, whereas the cold core and its smoothed curvature remain anchored by geometry and by the beam. The planetary scale observation that the largest modes are few and carry cosmic variance sets a quiet limit on how far any local refinement can push certainty. No increase in spectroscopic density, no improvement in shear calibration, and no extra year of microwave integration can produce a second independent sky. The residual's posterior therefore retains a width that is intrinsic to the problem. The same cold spot after subtracting a measured corridor still shares its angular scales with modes whose phases and amplitudes are drawn once. This limit is not an obstacle to understanding, it is part of the statement of results. It explains why the corridor's fraction can tighten markedly with better mass maps, while the residual's uncertainty shrinks more slowly and never vanishes. Looking outward across the sky, the Eridanus direction is not the only path through a wide low-density region, and the same analysis can be repeated elsewhere. Other corridors yield smaller deterministic templates and smaller residuals, and stacked profiles confirm the expected mean imprints. This repetition is important. It shows that the method works as a general tool, rather than as a bespoke explanation for one feature. The Eridanus case is simply the most prominent example of its class because the corridor is wide and the primordial draw is low at the same place. The consistency across corridors strengthens the inference that the cold spot's deterministic share is not special pleading. It is a measured component drawn from the same late-time physics that stacking and cross-correlations have mapped statistically for years. The practical path forward remains steady and observational. Spectroscopic programs tile the corridor more densely to reduce radial blur and to measure flows at void edges that confirm compensation. Weak lensing surveys deepen and widen to lower noise in tomographic convergence maps on degree scales. Multi-frequency microwave observations continue to stabilize large-angle baselines and to confirm frequency independence. Large-angle polarization maps refine dust templates that make temperature cleaning more robust. Simulations mirror the exact survey masks and beams, imprint measured corridors into structure realizations, and recompute conditional probabilities with the improved inputs. Each step lowers technical uncertainty in the corridor template and tightens the amplitude posterior around a value set by the measured mass deficit and by the known growth history. The residual contracts accordingly within the fixed cosmic variance floor. Against this schedule of refinements, the central picture is calm and stable. The cold spot toward Eridanus is a wide, smooth depression with a mild shoulder when read through a degree-scale beam. The nearby universe along that line of sight is underdense across a long path as mapped by galaxy counts corrected for bias and by lensing of background light. The evolution of gravitational potentials at late times shifts photon energies slightly as they cross such an underdensity, producing a small frequency-independent temperature decrement, whose shape is fixed by the corridor's projected geometry and by the smoothing beam. Subtracting a template built from the measured mass leaves a residual that is broad, smooth, and consistent with low multipole structure from the primordial background under the mask. Null tests, rotations, and control corridors do not overturn this partition. The numbers that summarize the split carry errors from measurement modeling and the sky's intrinsic variance, and they will tighten as maps deepen without changing sign. Placed back into the outer to inner structure that guides this account, the presence of alternative ideas, the reality of systematics, and the finite reach of statistics sit in clear order. Exotic causes are unnecessary because measured structure and known physics already account for a portion of the profile, and the remainder fits within the expected tail of a random field. Systematics are bounded by multi-field checks and reduced to noise floors. Statistics are handled with covariances that preserve what the sky can and cannot say. The result is neither a dismissal of curiosity nor an inflation of claims. It is the quiet completion of a line of sight where geometry, growth and smoothing explain shape, and where depth is shared between a corridor and the early field in proportions that data can now assign with measured uncertainty. Independent tracers that do not rely on maps of temperature or on lensing add depth to the Eridanus corridor without changing the calm outline already drawn. Peculiar velocities of galaxies provide one such layer. In underdense regions, matter flows outward from the centre towards surrounding filaments and sheets. Spectroscopic surveys that measure redshifts and for a subset dependent distance indicators can separate the Hubble expansion from local motions and recover coherent flows across tens to hundreds of millions of light-years. Along the Eridanus line of sight, velocities inferred from redshift space distortions show lower pairwise dispersions and mild outflows at the edges of the deficit, consistent with matter drifting away from the corridor's interior. The signal is modest because the underdensity is broad and shallow, yet the trend matches expectations. Void environments host coherent expansion that leaves a kinematic imprint even when density contrast is only moderate. These kinematics do not create the cold spot. They confirm that the corridor is a dynamical structure rather than a static artifact of selection. Star formation indicators add another quieter check. Galaxies in low-density environments tend to retain gas longer and show higher fractions of late-type morphologies at fixed mass. Along slices that cross the Eridanus trough color distributions tilt blueward by small amounts relative to control slices at similar galactic latitude, and emission line fractions rise gently where the density map dips. The change is not dramatic because the corridor is layered and because compensation spreads across depth rather than forming a sharp wall, but the environmental gradient is present and aligned with the mass maps. Integrated light from deep imaging, which traces diffuse stellar halos, and low surface brightness features also trends low along the corridor compared to denser directions at the same redshift range. These observations do not replace lensing or counts. They echo them with population-level differences that are characteristic of underdensity. Neutral hydrogen surveys extend the picture. Wide-area mapping of the 21-centimetre line can be stacked in broad redshift shells to trace gas-rich galaxies with less bias toward dense clusters. In the Eridanus direction, shell-averaged counts show a mild deficit that lines up with the corridor's redshift span, with a recovery toward the mean at edges, where compensation is inferred from optical samples. The neutrality of this line to dust and to stellar populations makes it a useful cross-check on selection effects in optical catalogues. Its agreement with the underdensity strengthens the case that the corridor is not a projection of missing light, but a genuine reduction in mass and galaxies. A different tracer, the kinetic Sunyaev-Zeldovich effect, offers a path that is subtle, but apt for wide regions. Free electrons moving with coherent velocities imprint small temperature shifts on the microwave background by Doppler scattering. In practice, the effect is sought statistically by correlating velocity reconstructions from spectroscopic surveys with microwave maps. For the Eridanus corridor, a stacked sign-sensitive analysis over the underdense slabs predicts only a faint average signal because electron densities are low where mass is low. The absence of a strong kinetic imprint thus supports the underdensity and does not conflict with the measured cold spot, which arises primarily from potential decay rather than from scattering. Any detection in the corridor would most likely appear at the edges where compensation lifts density and flows turn, and would be frequency independent in thermodynamic units, consistent with the filters already in place. Supernova Hubble residuals widen the crosscheck. Distances inferred from standardized candles when compared with redshifts can reveal coherent departures from the smooth expansion if many events lie behind the same large-scale structure. A supervoid like the Eridanus corridor alters the line-of-sight density only mildly, so the expected residuals are small. Nevertheless, compiling supernovae that project through the corridor and comparing their residuals with those outside provides a test for unnoticed calibration drifts or large peculiar motions that would argue against the quiet mass picture. Current compilations are sparse along this precise direction, yet within uncertainties they do not show a distinctive offset. The result is unsurprising given the corridor's breadth and gentle contrast, and it is consistent with a mass map that relies on galaxies and lensing rather than on rare candle alignments. Radio source counts present another frequency-independent tracer of mass on large scales. Bright radio galaxies inhabit massive halos, but also trace the cosmic web more broadly. After masking point sources used in foreground cleaning, residual catalogues can still be used statistically by counting sources in large apertures. Toward Eridanus, counts are modestly reduced compared with matched control regions in line with the general mass deficit. The correlation is weak because radio samples are sparse and inhomogeneous, yet the sign matches that of optical and HI tracers. This agreement across wavebands argues against a hidden frequency-specific foreground, shaping the cold spot, and supports a physical underdensity. A planetary-scale observation ties these cross-tracers together. None of them by itself carries the amplitude or coherence to explain the cold spot, but each reads the same corridor. Velocities flow outward, late-type fractions rise, neutral hydrogen stays modestly elevated where density is low, radio counts thin, and supernova residuals remain unexceptional. Lensing and counts continue to provide the core mass map. The others colour the environment in ways that fit a broad trough without forcing fine-tuned structures. Their coherence helps keep the interpretation within ordinary structure formation and away from specialised or singular causes. Simulations that include these observables close the loop between measurement and expectation. Light cone realizations seeded with initial conditions that match the large-angle power spectrum generate void complexes and filamentary walls across the same redshift range as the corridor. Semi-empirical assignments of galaxy types, star formation rates, and neutral gas to halos reproduce the observed environmental trends when tuned to match independent statistics. Line-of-sight projections through synthetic supervoids reveal temperature profiles with cold cores and faint shoulders, once potentials are allowed to decay with time and beams are applied. The corridor's measured width and contrast select the subset of lines of sight in which these profiles approach the Eridanus shape. The ensemble shows that templates built from mass maps should neither overproduce nor underproduce the shoulder when compensation is measured accurately, and that the remaining depth must vary with the primordial field just as the joint fit infers. Uncertainties that remain sit in technique rather than in physics. Neutral hydrogen surveys depend on flux calibration and on confusion corrections in crowded fields. Peculiar velocity reconstructions depend on distance indicators with their own biases. Weak lensing reconstructions at degree scales depend on shape calibration that drifts with size and surface brightness. Radio counts depend on completeness thresholds that vary with noise. Each of these is handled by survey teams with extensive null tests, and is incorporated into the corridor analysis through priors and error budgets. None points toward a hidden coherent systematic that could mimic both the mass deficit and the frequency-independent temperature depression with the same footprint and shape after smoothing. Their combined effect is to widen error bars in the corridor templates slightly, and by doing so to make the partition with the primordial residual more conservative rather than more confident. In the same calm frame, forecasts for next-generation surveys can be stated without speculation. Spectroscopy that extends to fainter galaxies over wide areas will carve the corridor into thinner slabs with measured velocities, at edges tightening compensation and reducing bias uncertainty. HI intensity mapping with larger dishes and lower systematics will track underdensities and their mild compensation across the same redshift range, with a tracer that is less sensitive to stellar population selection. Weak lensing maps with lower noise and better control of additive shear will deliver tomographic convergence on degree scales, isolating where compensation lifts and where it does not. Microwave experiments with improved large-angle stability will confirm the temperature profile's frequency independence and reduce residual baselines that enter the annular covariance. Together, these advances shrink measurement error in the template, while leaving the residual's cosmic variance floor unchanged, leading to a narrower, more precise statement of the corridor's fraction. The method's portability is another quiet strength. The same forward modelling likelihood and null tests apply to other wide underdensities where temperature profiles are milder. In those directions, templates remove small deterministic parts, leaving residuals that are correspondingly smaller. Applying the method across many corridors checks that amplitudes and shapes align with mass maps, and that no sky region demands special causes. The Eridanus case then sits at the cold end of a measured distribution of corridor plus primordial combinations, not as an isolated outlier defined by ad hoc steps. The repetition helps ensure that the joint fit used here is not tuned to one feature, and stabilizes the inference that the Eridanus cold spot is partly structural and partly statistical. The last observational niche is polarization at large angles. While the late-time temperature imprint is not accompanied by a strong unique polarization signature, careful mapping of polarized dust helps guarantee that temperature cleaning remains robust. In addition, cross-correlations between temperature and the